Okay, 4C, 42C. So we're in the last part of this section. So we're going to talk about linear and angular speed. So we'll be looking at like those two things really. That's kind of what we have to compute. And then there's a little bit of dimensional analysis that goes along with it when we're converting from different rates. Okay, so what is linear speed? So this is the speed at which an object moves along a circular path. Okay, so we've been dealing with rotational trigonometry and angles like that. So speed now, to calculate the speed, how it moves, that rate, the linear speed would be how it moves on a circular path. This is measured in certain units. It doesn't have to be miles per hour, but this is one of them that they're asking for. So they're measured in like something like miles per hour. Could be something different. Could be meters per second. Could be something else. So, and the next term is angular speed. Angular speed is the rate at which the object rotates about a fixed point. So it's going to rotate around the center is usually that fixed point, and which way it rotates around. And then this one, we measure this in revolutions per minute. It could be something different too. It could be revolutions per second, things like that. So again, it's usually measured in a unit, but you're going to have an answer of something per something, right? So you're going to have a miles per hour, right? Or revolutions per minute. So you're going to have that slash with something underneath it, basically what we're looking at there. Okay. All right, so let's focus on those in their formulas. So suppose an object moves at a constant speed along a circular path of radius s. So we've got that going. It's going along the circular path. So if this radius were just kind of travel around and around and around and around here, what would it be doing? Okay, so in that case, we call s. If s is the arc length, we can talk about the speed, and we're going to call it v for velocity, I think. So velocity, or we can just give it v. We already have an s too. That's the other thing. So if we used arc length, it's the s, so we can't use it for speed. So s is the arc length, and t is the time. Then the linear speed is measured by this. I mentioned that v in there. V equals s over t. That will give you linear speed. Then if we're talking about angle of rotation, if we've got theta is equal to the angle of rotation, and we again just keep in point out that this has to be in radians, okay, through which the object moves, again, another time t. Then the angular speed, it looks like a W. It's a weird looking W. It's a Greek W. That stands for omega. Omega is this little W. And you could say W, you could say omega. That's fine by me, okay? Either one. And that's given by this equation here, that W or omega equals theta over time, okay? Or equals the angle of rotation over time, right? Because theta is the angle of rotation. Okay, so let's work through a few of these problems, and then we'll see where we're at. All right, so we have a bicycle, and so you're riding the bicycle looks like this. And during one delivery, the tire rotates at about 440 revolutions per minute, okay? So find the angular speed of the tire in radians per minute, okay? So angular speed, we're looking at this formula here, the second one, the omega equals theta over time t. Okay, but there are a few things we have to look at first, okay? So just kind of putting some things together from the previous parts of the section. So if we know that a full rotation, if I go all the way around here, well, in radians, that's going to be 2 pi, right? A full rotation is 2 pi. So we know that also. Another thing to check out is right here. This is telling us the diameter is 30. So our radius, if we need a radius, would be 15. You might not need it here in part A, but you might need it in part B. So taking a look at it, we got to find out what theta is. We also know this is radians per minute here. So per minute, so that's going to be my time is going to be 1 minute basically. So now I really just have to find out the revolutions and what that is. So if it goes 140 revolutions per minute, so I can basically say that theta, or my angle of rotation okay, is going to equal, well, that 140 per minute, right? Times, well, what does it go? Every rotation is 2 pi. That's why we kind of figured that out over here. So really what it is, it's going to be about 280 pi radians. Okay. So plugging that in here, I can easily get my answer of W equals 280 pi radians per 1 minute. Okay, which if you wanted to go further, we could say, 280 pi basically. Or if you calculate that out, it's about 879.6 radians per minute, right? We talked about how there would be a per there. Okay, so that would be our answer there. All right, going to part B. On part of the trip of the next delivery, the tire turns at a constant rate of 2.5 revolutions per second. So a little bit different. So this was 140 revolutions per minute up here. Now we're talking 2.5 revolutions, but we're also talking per second. Okay, and now we want the linear speed of the tire in miles per hour. So lots to unpack here. All right, so let's first look at that. So we want linear speed. So linear speed is V equals S over T. Okay, so S, I need to find my S. Well, if I recall from the previous lesson, S equals R times theta, the radius times the theta. So here's where I'm going to need that 15. Okay, now I'm also going to need my new theta. Well, my new theta is 2.5 revolutions per minute. So 2.5, or per second, I should say. But remember, every rotation around is 2 pi. So that's actually going to be 5 pi rotations. So when I plug that in now, I can actually say that V is equal to, R times theta, because that would be equal to S, right? Over my time T, okay? So my R, so rewrite that because I don't like the way it looks. V equals R theta over T, right? Because this is equal to S, right? And so that's going to be 15 for my radius, right? We said that right up here on the first part of the problem, times the 5 pi for the rotations right there. And that's going to be over 1 second. Okay, so when we multiply that out, we get 75 pi. And we were talking about inches, right? Because the reason we're talking inches is because the radius here is in inches. So it would be inches per second. Okay, so a lot of people think we're done right here, but we're not, because remember, they want the answer in miles per hour. So that's where we have to be careful with what we're dealing with. How did I know we're dealing with inches again? Just to review, it's inches per second because I wanted to find it per second. I was dealing with 2.5 revolutions per second, but the radius that I needed right here is in inches. So inches, I got 75 pi inches per second. So now I have to do a little dimension analysis, which we talked about. So some people are better than this than others of doing this in their head, but it can also get a little bit crazy if you're not quite ready for it. So I just like to draw it out sometimes, and I'll show you that way, and you can do that. But if I have 75 pi, and this is inches per second. Now this is going to be a long one because we've got to go from inches to miles, and then we've got to get from seconds to hours. We want the answer in miles per hour. Okay, so we've got to go inches to miles, and then seconds to hours. Okay, so let's first start out with that. So I've got this, and I can multiply. I know that there's 60 seconds, so I'm looking to cancel, right? 60 seconds in a minute. Okay, and then I've also got 60 minutes for every second. Okay, and then I've also got, so that's going to get me to kind of minutes. Oops, I started that, screwed that up. It's 60 minutes in every hour, I should say. Okay, and then that kind of gets us to the hours, from seconds to hours, but now I have to go from inches to feet. So I've got 1 foot for 12 inches, and then I've got 1 mile is 5,280 feet. Okay, so with all that said and done, what we're going to do is, if I take this, and I can do some canceling here, because that's why I set it up the way I did. Okay, so I just moved it down a little bit so I had a little bit more space. But so the reason I did that is because, remember, I want to end up with miles per hour. So I wanted to get miles on the top, and on the bottom, I wanted per hour, because I want hours along the bottom. Okay, so that's what I'm looking for. So in this case, I can look to cancel. I've got seconds here, seconds here. I've got minutes here, minutes here. I've got hour here. Oh, don't need hour. I don't want to cancel out hour, because that's what I'm looking at. I got inches here. I've got inches down here. I've got feet here and feet here. So I'm left with miles on the top, and I've got hours on the bottom. That's what I wanted. So now I'm basically just calculating this out. 75 times 60 times 60 divided by 12 times 5,280. Okay, when you do that, you get about 13.4 miles per hour. Okay, using your calculator, multiplying across the top, and then divide it by these two multiplied here at the bottom. Dimensional analysis to get it to the rate they want. All right, so a couple more. First one, we've got this DVD over here. Find the angular speed of the DVD in radians per second if the disk rotates at a rate of 3.5 revolutions per second. So again, for part A, what I'm trying to do here is I'm going, this is what I'm finding angular speed. So W, or omega, equals theta over time. Okay, so my angle of rotation, that's my theta. It's 3.5 revolutions per second. And remember, each revolution, each rotation is 2 pi. So that's going to be 7 pi. And the time says per second here. Okay, so I can simply plug that in, and I'm going to get 7 pi per second, basically. Okay. Or since we're talking radians there, if I did 7 times pi, it would be about 22. I think there's a little bit of change, radians per second. So pi radians per second. Okay. So that would be, either one of those would work. I like it with pi. Pi is the exact value because we're rounding if we use the other way around. All right, now part B talks about this. So part B says, if the DVD player overheats and begins to rotate at a slower speed, so now it's going 3 revolutions per second instead of 3.5, find the disk linear speed, and then they want it in meters per minute. So we can find out the linear speed, which is V equals S over T. Okay, and again, remember that S is equal to the radius times the angle. But now our angle is a little bit different, right? Because now our angle, since it's now down to 3 revolutions per second instead of 3.5, so it's going to be 3 times 2 pi, because again, rotating around 2 pi. So now that's going to equal 6 pi. So I've got that. Now I need my radius, right? My radius here, since the diameter is 120, my radius is 60 millimeters. But be careful. Now we see we're going to have to do some dimensional analysis because they want the answer in meters per second, and we got to get from millimeters, or they want meters per minute, and we got to get from millimeters per second. Let's just calculate this out, and then we can do the analysis afterwards. So this is going to basically equal 6 pi times my radius of 60 is going to give me, and of course divided by t, which is in this case 1 second, is going to give me 360 pi radians per second. Okay, so that's fine in radians per second. However, we need to go from there to meters per minute. So to do that, I'm going to do my little dimensional analysis here. It's not as long as the last one. So we've got 360 pi over, that's millimeters per second per 1 second. Okay, so when I'm doing this, I can go here and say, all right, 60 seconds in a minute. So now that's what I wanted to do. I wanted to get to minutes. I'll be able to cancel those out. And then I've got to do one more thing, right? I've got minutes along the bottom, but I need meters along the top. So 1 meter is equal to 1,000 millimeters. So then when I go into canceling here, I can cancel out my seconds here and seconds here. I can cancel out my millimeters here, millimeters here, and I'm going to get 360 times 60, but then I'm going to divide it by 1,000. And then I have pi involved in there too, so I end up getting 67.9 meters per minute. And again, to calculate that out, I took 360 pi times 60 times 1, and I divided it by 1,000 because of times 1 times 1 to get that. Okay? You could do it a different way too, right? There's another way. If I just change this, if I saw this was in millimeters and I wanted to change it, it would make it a little bit, different. I'd have to change this into 0.06 meters to do that, right? And then I could factor it in the original equation, but I also would have to change this from seconds to minute. So whatever works, if you're good at doing that, go ahead and do that the other way. But if you can cross-cancel a dimensional analysis, you're fine. All right, one more. Number 3. So it wants the angular speed. We got a typical vinyl record, diameter 30 centimeters. Played on a turntable, the record spins at 33.1 revolutions. Okay, so again, just going through it, I want the first one says find the angular speed. So angular speed is theta over time. We've done that. So I've just got to find, I know my time is 1 minute. I've got to find my theta, which is going to be 33 1/3 times 2 pi because of the rotation. So I end up getting here 209.4 radians per minute. Or you could write it like this, right? Okay, so that was the easy part. Now for B, says that find the linear speed at the outer edge. So now we're talking linear speed as the record spins in centimeters per second. So what I'm doing here now is V equals S over T. But now, unlike the last problem, the speed didn't change. Speed stays the same. So the revolutions are the same per minute. So I've already got that right here. So I can bring that down, and that's going to stay as my theta, as my angle of revolution, because the speed didn't change. In the problem up here, the speed slowed down, right? But here it doesn't. So we can keep the same action there. Now we've got a radius to deal with, right? We said it has a diameter of 30 centimeters. So that means R equals 15 centimeters. So I've got my R of 15 centimeters. And remembering that S equals theta times R, I can just go ahead and say that this is 209.4 times 15, which gives me about 314.1 centimeters per minute, okay? Which is pretty good because my time I know was in minutes. But they want us in centimeters per second. So again, I'm going to have the dimensional analysis on this. It's a really easy one. It's really short. I go 314.1 centimeters over the 1 minute. Remember, I got to change from minutes to seconds. Centimeters, they want centimeters per second. So I don't have to change the centimeters at all. So really, I just have to say, all right, if I go this, 1 minute equals 60 seconds. So simply, or if you knew you could do this and just divide by 60, you're in good shape. So I could cancel here. I'm basically just taking 314.1 and divided by 60 to get 52.35 centimeters per second. And on those ones, since there's only one simple conversion, you might just take this and divide it by 60 and get there. If you can do that, if you do that in your head and you know that. Okay? All right. That is 4-2C, and that's 4-2, the end of it. So bring questions, and we'll work on it